Hey everyone, so welcome back to the next video, which is about binary multiplications. So before I go into the shifts and addition process, I want to show you how it works for smaller binary numbers. So the traditional multiplication. In the last video, we learned about converting from decimal to binary, binary to octal, and all different bases to different bases using division algorithm or expansion. And we also learned how to add two values in different bases. You just convert the individual sum and operate the regular sum in like you do in real life. So traditional multiplication also works the same in binary. Suppose I have 101 in binary and I want to multiply it by 10. Okay, how does it work? 101 times 10, multiply as usual. And you're like, is it a joke? No, it is as simple as that. Write 0101 and that's the answer, right? But multiplication is longer. So there is this method called shifts and addition that we will use in this course. You might get a few conceptual type questions in exams. I will not ask you to repeat this process for longer binary numbers in exam. So, but how do I verify my answer here? What is 101? 101 in binary is 5 in decimal, right? Because it's 1 times 2 to the 3, 0 times 2 to the 2. Oh, wait. That's why I always start with the last entry. 1 times 2 to the power 0, which is 5 in decimal. And what is 10 in binary? 10 is 3 in decimal, right? And what is 5 times 3? 5 times 2? 10 is 2 in decimal. My bad, 10. And you can check 1010 is in binary is 10 in decimal. So we can verify our answer too. Now, what about the shifts and the addition process? So the left shifts and the right shifts work the same way. Once you understand one concept, you'll be fine with the other one too. Multiplication in base 2, multiplication in base 2 using shifts and addition. So left shift, right shift works the same. Suppose I'm multiplying a binary bit which has n digits or n bits as we call it by another binary number which has n bits again, say. Okay, so this is how you start the process. You look at the q value and number one, steps for multiplication. If your bit is zero in Q, all you do is perform a right shift. Perform a right shift. Okay? And if your bit is 1, then you add Q is 1 in, I'll do an example in a minute, but you have to remember these two processes. Okay, this is how computer multiplies in binary, and that's why it's faster. Computer does the shifts and addition. That's why it doesn't do the traditional multiplication, because for longer binary numbers, which you can imagine, because decimals converted to binary are huge, computer needs to do this to make it faster, because adding and shifting is way faster than traditional multiplication. So if bit is 1, then you add M to the register. Now register is the highest number of bits that can possibly happen. So suppose I have this example. Okay, I'll start with an example, then I'll go back to the notes. This is extra. This is just, FYI, you should know this. That's why I'm recording a video on this. If your M is 1010, Q is 0110. Okay, and I want to find M times Q. because M has 4 bits and Q has also 4 bits, the maximum bits in M dot Q can be 8. Okay, it can only have more, it cannot have more than 8 bits. So I'm going to start with 8 zeros because that's the maximum number of digits I can have in my product. So look at the last digit, look at Q, okay, and start from the end. This bit is 0. What does that mean? So step 1, I will perform a shift, a right shift on the register. A right shift means nothing changes, it stays 0, right? Now, the second one is a 1 again. So what's the answer? What happens when I have a 1 in the queue? I add M to the register. So I'm going to add M to the register again. So every 0 remains as it is. And there you go. So the answer is 1010 0000, right? And the third one is a 1 again. So what do I do? Oh, sorry, I forgot. If the bit is 1 in Q, add M to the register, then perform a right shift. I was like, this doesn't look right. Then perform a right shift. Okay, so you add and you perform a right shift. I added, but I still have to do a right shift. So everything shifts to the right. So I got a 0 1 0 1 0 0 0 0. Okay, it's just moving in cyclical order. Now let's move back to the third entry, which is 1 again. So I should add M again. So I'm adding M again, and this will be 1 plus 0 is 1, 1, 1, 1, 0, 0, 0, 0, right? And again, I have to shift because if you have a 1 in your queue, you add and then you shift again. So 0, 1, 1, 1, 1, 0, 0, 0, right? And then I have a 0 at the end. So I just need to perform a shift. So it will be 0, 0, 1, 1, 1, 1, 0, 0. Now you can remove all extra zeros in the front. So M dot Q in binary will result in 1, 1, 1, 1, 0, 0 in binary. Now I know this is still, it's faster for the computer, but still it's tedious, right? But the only conceptual question that I'll ask you in the exam is this type of questions. I won't ask you to multiply binaries this big, right? But I might ask you, how do you work these questions? Let me find my notes again. So let's go back to the multiplication, right? This is the example that we did on the other page, right? This can be done using binary, or this can be done by shifting. But the question is, suppose I can express this. I have this one, right? Which can be expressed as 1000 plus 10 plus 1. So what does it mean? I have 1 0 1 1 0 1 3 zeros, right? Then I add this again with 1 0. Sorry, I need to find my notes so I don't give you the wrong answer here. Yeah. Then I only have 1 0 extra, so I'll do 1 0 1 1 0 1 0, and the last one I copy it again. So I'll have 1 0 1 1 0 1, and I add. So what is the answer? 1 plus 0 is 1. It's 1. 3 is 11 in binary. So 3 will give me 11, carry 1. 1 plus 1 is 2. 2 is 10 in binary. And this is also faster. So this will be 10, carry 1. 1 plus 1 plus 1 is 3, which is 11 again, carry 1. 3, 11 again, carry 1. 1 here, which will be 1 and 1. So this is the answer. So you can either do the shift and additions, but this is what you are supposed to do. Like you can also multiply this. Now, this is very time consuming and this is pretty useless because the computers are doing this for you. But you must know how many shifts I need to perform. So if I'm multiplying m dot q, how many left or right shifts do I need to perform? I need to perform a shift. If I go back to the steps, I need to perform a shift in every step, right? Even if the bit is 0, I need to perform a shift. Even if the bit is 1, I have to add m, then perform a shift. So if I have m dot q, then the number of shifts is the same as size of q, or the number of bits in q. So if I'm doing, say for example, 10111 times 1000, well, it should be bigger than this one, right? 1. So the number of shifts I'll perform is 1, 2, 3, 4, 5. I'll perform 5 shifts. Okay? Because I have 5 bits in my queue. How many additions? You only add when you get a 1. So addition is the same as number of ones in queue. So in this case, number of additions will be 2. There will be 2 times you'll add. Make sense? But you'll shift this many times. So if you try to break it up and do partial sum approach, this is called breaking up the queue and doing partial sum. The partial sum approach. This is also fine with me. You can do this and works perfectly. And this is it. This is all that I need to cover for binary and decimal and integer representation in different bases. Now we'll do a nice application, which is fast modular exponentiation in the next video.